In March of 2015, American astronaut Scott Kelly and his Russian colleague Mikhail Kornienko began an unprecedented mission in space. They began a one-year term of service aboard the International Space Station, the longest tour of duty ever served on the ISS. Now, I imagine there's all sorts of stuff to worry about when you're packing for a year-long space voyage, like, say, how many books should I bring? How many pairs of underwear? Am I really okay with pooping into a suctioned plastic bag every day for a year? Will I come upon a derelict ship haunted by some stranded and insane astronaut from a forgotten mission, like in pretty much every space horror movie ever? Will there be coffee? Reasonable questions all, but in reality, another one you might want to ask is, will I be able to walk when I get back home? We know microgravity is hard on a body, and this mission is largely about testing the physical effects of being weightless for so long. Astronauts often experience things like trouble sleeping, puffy faces, and loss of muscle mass, but perhaps the most serious damage a microgravity environment causes is to the bones. And bones, well, they're pretty clutch. So they may look all dried up and austere. Don't be fooled. Your bones are alive. Alive, I tell you. They're actually as dynamic as any of your organs and are made of active connective tissue that's constantly breaking down, regenerating, and repairing itself throughout your lifetime. In fact, you basically get a whole new skeleton every 7 to 10 years. In short, your bones do way more than just providing your squishy sack of flesh with support and scaffolding and the ability to move around. Your bones are basically how you store the calcium, phosphate, and other minerals you need to keep neurons firing and muscles contracting. They're also crucial to hematopoiesis, or blood cell production. All of your new blood, and we're talking like 1 trillion blood cells a day, is generated in your bone marrow, which also helps store energy as fat. Bones even help maintain homeostasis by regulating blood calcium levels and producing the hormone osteocalcin, which regulates bone formation and protects against glucose intolerance and diabetes. So the big buzzkill about life in space is that up there, a person suffers 1 to 2% bone loss every month. By comparison, your average elderly person experiences 1 to 2% bone loss every year. So for Kelly and Kornienko, that could mean losing up to 20% over a year in orbit. Given everything your bones do for you, that's really serious. And while most of that loss is reversible once they're back on Earth, it's not as easy as chugging some of Madame Pomfrey's Skelegro potion. Rehabilitation can take years of hard work, and that's after just a few months in orbit. Which is why Kelly and Kornienko are heroes of science, and not just for scholars of anatomy and physiology everywhere, but for anybody who has bones. An average human body contains 206 bones, ranging in shape and size from the tiny stapes of the inner ear to the huge femur of the thigh. That's a lot of bones to keep tabs on, so anatomists often divide these structures first by location into either axial or appendicular groups. As you might guess, your axial bones are found along your body's vertical axis, in your skull, vertebral column, and rib cage. They're kind of like your foundation, the stuff you can't really live without. They carry your other body parts, provide skeletal support and organ protection. Your appendicular bones are pretty much everything else. The bones that make up your limbs and the things that attach those limbs to your axial skeleton, like your pelvis and shoulder blades, these are the bones that help us move around. From there, bones are generally classified by their shape, and luckily those names are pretty obvious. Long bones are your classic-looking dog bone-shaped bones, the limb bones that are longer than they are wide, like the tibia and fibula of your lower legs, but also the trio of bones that make up your fingers. Follow some of those long bones to your foot or hand, and you'll hit a cube-shaped short bone like your foot's talus and cuboid, or your wrist's lacunate and scaphoid. Your flat bones are the thinner ones like your sternum and scapulae, and also the bones that make up your brain case. And your irregular bones are all the weirdly shaped things like your vertebra and pelvis, which tend to be more specialized and unique. But despite their variations in size, shape, and finer function, all bones have a similar internal structure. They all have a dense, smooth-looking external layer of compact or cortical bone around a porous, honeycomb-looking area of spongy bone. This spongy bone tissue is made up of tiny cross-hatching supports called trabeculae that help the bone resist stress, and it's also where you typically find your bone marrow, which comes in 2 colors, red and yellow. Red marrow is the stuff that makes blood cells, so you should be glad that you have some of that, and yellow marrow stores energy as fat. If you happen to be a predatory animal, yellow bone marrow can be one of the best sources of calories you can find. The arrangement of these bone tissues, though, can be slightly different from one type of bone to the next. In flat, short, and irregular bones, for example, these tissues kind of look like a spongy bone sandwich on compact bone bone bread. But in some of your classic long bones, like the femur and humerus, the spongy bone and its red marrow are concentrated at the tips. These flared ends, or epiphyses, book into bone's shaft, or diaphysis, which instead of having spongy bone in the center, surrounds a hollow medullary cavity that's full of yellow marrow. Now, although bone can look rock solid, grab a microscope and you'll see that it's actually loaded with layered plates and laced with little tunnels. It's intricate and kind of confusing in there, but the more you zoom into the microanatomy of bones, the better you can see how they're built and how they function right down to the cellular level. Let's start with the basic structural units of bone called osteons. These are cylindrical weight-bearing structures that run parallel to the bone's axis. Look inside one and you'll see that they're composed of tubes inside of tubes, so that a cross-section of an osteon looks like the rings of a tree trunk. Each one of these concentric tubes, or lamellae, is filled with collagen fibers that run in the same direction. But if you inspect the fibers of a neighboring lamella, either on the inside or the outside of the first one, you'll see that they run in a different direction, creating an alternating pattern. This reinforced structure helps your bone resist torsion stress, which is like twisting of your bones, which they experience a lot, and I encourage you not to imagine what a torsion fracture of one of your bones might feel like. Now, bone needs nourishment like any other tissue, so running along the length of each osteon are central canals which hold nerves and blood vessels. And then tucked away between the layers of lamellae are tiny oblong spaces called lacunae. As tiny as they are, these little gaps are where the real work of your skeletal system gets done, because they house your osteocytes. These are mature bone cells that monitor and maintain your bone matrix. They're like the construction foreman of your bones, passing along commands to your skeleton's two main workhorses, the osteoblasts and the osteoclasts. Osteoblasts, from the Greek words for bone and germ, or sprout, are the bone building cells, and they're actually what construct your bones in the first place. In the embryonic phase, bone tissue generally starts off as cartilage, which provides a framework for your bones to grow on. When osteoblasts come in, they secrete a glue-like cocktail of collagen, as well as enzymes that absorb calcium phosphate and other minerals from the blood. These minerals form calcium phosphate, which crystallize on the cartilage framework, ultimately forming a bone matrix that's about 1/3 mineral, 2/3 protein. From your time in the womb until you're about 25, your osteoblasts keep laying down more collagen and more calcium phosphate until your bones are fully grown and completely hardened. So while your osteoblasts are the bone makers, your osteoclasts are the bone breakers, which is kind of a violent image. Maybe think of them as like a bone breaker downer. Although the two kinds of cells do exact opposite jobs, they're not mortal enemies. In fact, I'm happy to report that they get along fabulously and create a perfect balance that allows your bones to regenerate. It's like if you want to renovate your house, you gotta rip out all those busted cabinets and the musty carpeting before you can bring in the nice hardwood floors and custom countertops. These cells work in a kinda similar way, in a process that I'd argue is less stressful than home improvement. It's called bone remodeling. The supervisors of this process are those osteocytes, which kick things off when they sense stress and strain or respond to mechanical stimuli, like the weightlessness of space or the impact of running on pavement. So say you're out running and something happens, nothing to be alarmed about, but suddenly the osteocytes in your femur detect a tiny microscopic fracture and initiate the remodeling process to fix it up. First, the osteocytes release chemical signals that direct osteoclasts to the site of the damage. When they get there, they secrete both a collagen-digesting enzyme and an acidic hydrogen ion mixture that dissolves the calcium phosphate, releasing its components back into the blood. This teardown process is called resorption. When the old bone tissue is cleaned out, the osteoclasts then undergo apoptosis, where they basically self-destruct before they can do any more damage. But before they auto-terminate, they use the hormone hotline to call over the osteoblasts, who come in and begin rebuilding the bone. The ratio of osteoclasts to osteoblasts can vary greatly, and if you stress your bones a lot through injury, by carrying extra weight, or just normal exercise, those osteoclasts are going to be swinging their little wrecking balls non-stop, breaking down bone so it can be remade. In this way, exercising stimulates bone remodeling and ultimately bone strength. So when you're working out, you're building bone as well as muscle. Which brings us back to our two space heroes / guinea pigs, Scott Kelly and Mikhail Kornienko. Space crews generally need to exercise at least 15 hours a week to slow down the process of bone degradation, but even that can't fully stave off loss of bone density. In microgravity, osteocytes aren't getting much loading stimuli because less gravity means less weight. But for reasons that we don't understand yet, the osteoclasts actually increase their rate of bone resorption in low gravity, while the osteoblasts dial back on the bone formation. Because there's more bone breaking than bone making going on, everything is out of balance, and suddenly people start experiencing 1 to 2% monthly loss in bone mass. gas. So in addition to providing astronauts with oxygen and water and food and protection from radiation and an environment that will keep them mentally stable, it turns out that we also have to figure out how to keep their bodies from consuming their own skeletons. But at least today we learned about the anatomy of the skeletal system, including the flat, short, and irregular bones and their individual arrangements of compact and spongy bone. We also went over the microanatomy of bones, particularly the osteons and their inner lamella. And finally, we got an introduction to the process of bone remodeling, which is carried out by crews of osteocytes, osteoblasts, and osteoclasts. Special thanks to our headmaster of learning, Thomas Frank, for his support for Crash Course and free education. And thank you to all of our Patreon patrons who make Crash Course possible through their monthly contributions. If you like Crash Course and you want to help us keep making cool new videos like this one, you can check out patreon.com/crashcourse. This episode was co-sponsored by the Midnight House Elves, Fatma Iqbal, and Roger C. Rasha. Crash Course is filmed in the Dr. Cheryl C. Kinney Crash Course studio. This episode was written by Kathleen Yale, edited by Blake DiPastino, and our consultant is Dr. Brandon Jackson. Our director is Nicholas Jenkins, the editor and script supervisor is Nicole Sweeney, our sound designer is Michael Ronda, and the graphics team is Thought Cafe.